What up, homies? You're about to get your minds blown, Group B28 style. Are you ready? Buckle your seatbelts for direct proofs. Bing.
Okay. Hey, no, go. That was ridiculous. Alright, actually, now to the actual stuff. A direct proof determines whether a given statement, P implies Q, is true by using established facts, previously proven theorems, and rules of inference, without making further assumptions. The first step of a direct proof is to always assume that P is true. Then we form a logical argument using established facts to come to the conclusion that Q is also true. Essentially, in a direct proof, we must show that Q is never false when P is true. We can sufficiently do so by proving that when P is true, Q must also be true. Alright, to an example. For this example, we want to use a direct proof to show that if A is an odd integer, then if an integer is odd, then it is also the difference of two squares. First, we want to assume that A is an odd integer. By the definition of an odd integer, A must equal 2B plus 1, where B is any integer. The difference between two squares, B plus 1 quantity squared minus B squared, is equal to B squared plus 2B plus 1 minus B squared. This simplifies to 2B plus 1. This is the same as A. Therefore, it is an odd integer. Through this, we have directly proven that for every odd integer, it is also the difference of two squares. Going on, what makes a proof direct is its first step, which always assumes that the premise P is true, and its method of using only established facts, no assumptions. In this way, direct proofs differ from indirect proofs, which begin with some hypothetical scenarios. Some forms of direct proofs include proof by induction, which proves that in an infinite sequence of statements, if one statement is true, then so is the next. The other form of a direct proof is proof by cases, which proves that the premise holds for a finite number of cases. For example, if you want to prove that a statement P implies Q for all integers, it is sufficient to first prove that P implies Q holds for all even integers. And then to separately prove that this premise P implies Q holds true for all odd integers. Through this, we have proved that for all integers, P implies Q. This is how you do a direct proof by case. To recap, the basic form of all direct proofs is to first assume that the premise is true. Then you must prove that the conclusion must also be true by using existing facts, previously proven theorems, and rules of inference. The rules of inference can be found on your textbook on pages 69 through 71 and include laws such as the identity law, the distributive law, and the associative law. And remember, make no assumptions except for the premise. Alright, now to another example. In this example, we want to show that if A is an even integer, then the square of A is also an even integer. First, we assume that A is an even integer. By the definition of an even integer, a is equal to 2b, where b is any other integer. When we square a, we also square the quantity 2b. This is equal to 4b squared. 4b squared is also a factor, is a multiple of 2. And so that is equal to 2 times the quantity 2b squared. Since it is a multiple of 2, it is an even integer by definition. Therefore, the square of an even integer is a is also an even integer. Notice once again that the first step assumes the premise is true, and that our following steps come from the definition of an even integer and the rules using multiplication and factoring. Alright, let's go to one final example. For this example, we want to show that the sum of two odd integers is even. First, we assume that a and b are odd integers. As previously said, the definition of an odd integer is that it is equal to an integer times 2 plus 1. So in this case, a is equal to 2c plus 1, and b is equal to 2d plus 1. When you add a and b together, this is equal to 2c plus 1 plus 2d plus 1. This is equal to 2c plus 2d plus 2. You can factor out a 2, and what's left is c plus d plus 1. So therefore, the quantity is 2 times c plus d plus 1. Since this quantity is a multiple of 2, it is an even number. Therefore, the sum of two integers is always even. This is a lesson on direct proofs from B28. I hope you enjoyed it, and have a nice day.